All right, welcome back. In this video, we're going to go over E2 reactions. We made it to 100,000 views. Thank you so much. Imagine if this was 100K subscribers. Subscribe and like and share. Okay, so before we went over substitution reactions, and remember, substitution reactions, we replaced the leaving group with a nucleophile. In elimination reactions, what we do is we eliminate the alkyl halide, which is basically a carbon with a halogen attached to it, and what we're doing is replacing it with a double bond. Okay, so elimination reactions is all about making double bonds. We're not putting anything on the molecule. The only thing we're putting on the molecule is a double bond. That's it. Substitution reactions like SN2, SN1, we are physically putting the nucleophile onto the molecule. Here, we're just adding a double bond. But the big question in this entire video is, where do we put the double bond? And I promise you, I made it so easy, okay? But we need to get over the basics first. So what do we do? What is this? What am I talking about? So elimination reactions, E2 in specific, what we're doing is we're using a base, and the base eliminates the halogen in our molecule and replaces it with a double bond. Okay, but how do we do this? There are a few components you need to know. The first thing is when you're given a molecule, you'll notice that there's going to be a halogen attached to it, okay? The halogen is attached to the alpha carbon. So once again, what it is the alpha carbon is the carbon that the halogen is attached to, okay? There's also something called the beta carbon. The beta carbon is directly adjacent to the alpha carbon. It's directly bonded to the alpha carbon. So it's just another carbon that's right next to the alpha carbon. Now this beta carbon is essential to do this reaction because attached to the beta carbon must be a proton. What we do is we essentially use the base to sacrifice a proton to put a double bond onto the molecule. Okay, so this is what the overview of the reaction is. This is just a general elimination reaction. This applies to E2 and E1 reaction. Basically, what happens, the base comes along and steals the proton, okay, which is indicated here. The bond that was between the carbon and the proton now transfers electrons in the middle between the alpha and beta carbons. This is really important to know. When this happens, a double bond forms between the alpha and beta carbons, nowhere else, okay? Always between the alpha and beta carbons, okay? But when this happens, so let me draw this in. When this happens, you will notice that this carbon now, the alpha carbon, which has the halogen attached to it, now has 5 bonds. This is illegal. It has, let's see, let's take a look. 1, 2, because of the double bond we just created, 3, 4, now 5. 5 being the halogen. So what happens is the carbon realizes that it needs to kick something out. So it'll kick out the halogen. So it's set free, which is indicated here at the end of the reaction. So we are left with a double bond between the alpha and beta carbon, right? This is the alpha, this is the beta. We are now left with a double bond between them. The base has now stolen the hydrogen, the proton, and we have set free the halogen, okay? That is what a basic elimination reaction is. So let me go over what an E2 reaction is then. All an E2 reaction is when we put the stuff in the beaker, right? We put the substrate in the beaker, then we put the base. The entire reaction happens instantly, all at once. Whereas in E1 reaction, things will take place step by step. So in E2 reaction is what we call a concerted mechanism, and an E1 reaction, which will be probably next video, is called a stepwise function because a stepwise mechanism happens in steps. So what happens in the arrow pushing is the base uses its electrons to basically steal the proton away from the beta carbon. The bond, once again, dissociates and forms between the alpha and beta carbons, and carbon's like, wait a second, I have an extra bond. I have 5 bonds. That's not allowed. So let me kick this halogen away and set it free. Okay? So the big question is when do we use E2 reactions? You will use an E2 reaction when the substrate you are dealing with, right, the main molecule in question, is a second degree or third degree. And a second degree or third degree alkyl halide to be specific. So that is when the alpha carbon has either 2 or 3 branches attached to it. Okay? 2 or 3 R groups. And you have a base as well. So you must have a base. A nucleophile will not do. It has to be a base. Now, you can also do it on first degree alkyl halides. You can do it on first degree alkyl halides only if the base is bulky. And you're probably wondering, what is that? So let's go over common bases you will see. So on an exam, or when you do practice problems, one of the most common bases you will see is sodium ethoxide. Okay? Sodium ethoxide is not a bulky base. So whenever you see sodium ethoxide, it will work when you have a second degree or third degree alkyl halide. Same will go for sodium methoxide. What sodium ethoxide is basically an ethyl group bonded to the oxygen, and sodium is there as well. Sodium methoxide is a methyl group with an oxygen and sodium, okay? Another one you'll see is sodium hydroxide. This is also not a bulky base, so you will use it in a second degree or third degree alkyl halide. Okay, so remember, these are all bases. Another one you will see, which is quite common actually, is tert butoxide. This is a bulky base, so you are able to use it if you see a first degree alkyl halide. It's legal, okay? You can also technically use it for second degree and third degree, but mainly you'll use these. Okay, so this is tert butoxide. Basically, what it is a potassium, and then you have a butyl group, which is basically like a tree branch, and an oxygen like that. That's what a tert butoxide is. Okay? Regioselectivity. Now, if there's anything you need to take away from this video, this is it right here. You will be tested on this 1,000,000%, because they're forced to test you on this. Okay, I had a bunch of questions about this when I took Ochem 1. Okay, so unfortunately for us, elimination reactions can give us 2 different products. So, for example, here we have the alkyl halide, right? So this is obviously the alpha carbon because this is the carbon that has the halogen attached to it, okay? That would mean that the adjacent carbons would be beta carbons. Also this one as well, this would be a beta carbon, but for simplicity, I did not include it. So you have the alpha carbon here, and we have 2 beta carbons. And remember, I said in elimination reactions, we create a double bond between the alpha and beta carbons. So we eliminate the halogen, right, this alkyl halide, so we remove this completely, and then we put a double bond between either of the beta carbons, right, alpha beta carbon. But the big question is where do we put the double bond? Do we put it between this alpha and beta carbon, or do we put it between this alpha and beta carbon? That is the big question. So here we have this, right? We could have put, this is the alpha carbon, right? And this is the beta carbon. We put the double bond between that. Or we could do it here, right? If it looks confusing, remember, what we did is we eliminate this. This bond does no longer exist, right? So I just redrew it so this is sticking up for geometry reasons, right? So this is the alpha carbon, this is the alpha carbon, right? This is this, and this is this. I just drew it straight up, right? For geometry. And we eliminated this. So this is the alpha carbon, and this is the beta carbon. So I drew the double bond between there. But how do we know which one to draw? So there are things we need to talk about. And that is major or minor products and Zaitsev and Hofman products. It is very important to know, and a lot of organic chemistry students make this mistake. So you're not alone if you think this as well. They are not the same thing. there is a circumstance where they are, but people think that the major product and Zaitsev go hand in hand, and the minor and Hofmann go hand in hand as well. That is not always the case. Okay? It's very important. They are two different things, but they can be related. Let's talk about major and minor products first. So say when you mix the substrate and base together, right? We take a beaker, we put the substrate in, we put the base in. And you'll get two different products, right? We get this looking one and this looking one. The one that is the most abundant, right, is the major product. The one that is least abundant is the minor product. So say now we look in the beaker, we reach into the beaker, you shouldn't do this, and you fish out the two different products. The one that has the most abundance, the one we made the most is the major, and the one we made the least is the minor, okay? That is it. It has nothing to do with Zaitsev and Hofman just yet, okay? Now, let's talk about Zaitsev and Hofman. Basically, two guys that found this. When doing the reaction, you usually have two different looking products, right? Like this and like this. The one that is more substituted, or in other words, the one that has more R groups attached to the alkene, or in other words, the one that has more branches attached to the alkene is the Zaitsev product. The one that is less substituted, right, the alkene that is less substituted is the Hofmann product, okay? Now, usually, the Zaitsev product is the major product. However, if the base is bulky, the major product is the Hofmann product. Okay, so let me break it down in another way. So say if you go to a supermarket, okay? Say you go to Whole Foods, because we have a Lamborghini. This looks like, it should be a Lamborghini. No. Say you go to Air One, okay? Air One is a very overpriced supermarket located in California. Don't ever go there and waste your money. People buy these, like, okay, they have these famous smoothie there. It's called the Hailey Bieber smoothie, right? Which is like $20. Who would pay $20 for a smoothie? Like, that's a ridiculous amount of money. If you go to the Air One, you'll notice you can buy a gallon of milk for like $9. Why? It basically, don't ever shop there. Please save your money. Pay your tuition, pay for books, pay your housing, pay your rent. Don't go to Air One, okay? So, imagine you go to the supermarket, you go to Air One, you go to Whole Foods, whatever, and right next to the entrance, you see an open parking spot. This open parking spot is very nice, it's very convenient because it's close by to the entrance. It also it's illuminated by light, by street lamps, right? Lamps. It's very convenient. But the parking spaces are very narrow. So you must have a narrow car to fit in, okay? But this is the ideal parking space. This is what you want. This is like the Zaitsev product, okay? It's very favorable, in other words. This is what we usually want in most circumstances. The very convenient. Zaitsev is very convenient, okay? Because remember, when something is more substituted, it is more stable, it is more safe. This parking spot is safe, okay? In other words, now, say you have a big, huge ass SUV or one of those pickup trucks that are lifted. You won't be able to fit in that narrow parking space near the front of the store. So you have to park all the way in the back, right? So imagine your car is a very bulky base, right? It does not want to fit in the small parking spot. It's not really convenient. You still can fit in, but you have to go all the way to the back. It's not really ideal, right? It's kind of like Hofmann. It's not really ideal, not really stable. You don't really want to do that, right? It's not really safe. You could be mugged in the middle of the night walking to your car. But it's the only option you have because you have a big car, right? The big car is a big base, right? You're this Lamborghini. It's a very narrow, small car, right? That's a non-bulky base, right? It can fit nicely in, right, to the reaction. That's what's basically going on. Hopefully that was kind of easy to understand. It's kind of awkward, okay? So once again, the Zaitsev product is usually the major product, not always, right? It is not when the base is bulky. So for example, if you see tert butoxide, the Hofmann will be the major product, okay, not the Zaitsev. So if you were to get asked a question, given this reaction, draw the major and minor product, right? And please and indicate what the major and minor product is. And if you're given tert-butoxide and when you draw your little reaction, right, and you show the more substituted is the major product, you will get it wrong because tert-butoxide is. So let's go over some. Actually, first let's go over some bulky base examples. The very common one is obviously tert-butoxide. Like I said, it's the most common. I have been given these on tests. This is why I'm giving it to you. If you see a nitrogen here, that's the easy, immediate indicator that this is a bulky base. Okay, remember, the ones that are not bulky don't have any nitrogens in them. But these two do, okay? So this is your telling that this is a bulky base. So remember, tert-butoxide, most common, and then these two with nitrogens are also bulky bases. So whenever you see any of these in your reaction, the Hofmann is going to be the major product. So let's go over an example of how we accomplish a problem like this. Predict the major and minor products of this reaction. This is a very typical exam question. So here you have your molecule, right? And then we have our base, which is sodium methoxide. So already we know this is not a bulky base. This means the more substituted answer, alkene, is going to be the major product. So in other words, the Zaitsev, because remember, the Zaitsev means it is more substituted. It has more branches to the alkene. The Zaitsev product will be the major product. We already know that just from looking at this, okay? You don't need to look at the molecule at all. You just need to look at the base. First, identify all the beta carbons that have protons. So this is the first step. First, you need to identify what is the alpha carbon and what are the beta carbons. So remember, we're looking at this, right? So the alpha carbon is the one directly bonded to the halogen. Now, all the carbons adjacent to the alpha carbon are now all beta carbons, okay? So that's what I did. I just drew in a beta sign for all of them, okay? That's step one. Now, for step two, let me draw underline here. Okay. What you're going to do is draw all the possible products. Should be an S there. I should really spell check these. Okay. All you need to do is remove the alkyl halide and replace it with a double bond between the alpha and beta carbons. That's all you need to do. It's super easy. So, remember, this is the alkyl halide, right? We're going to eliminate this, wipe it out of existence, right? So that's what we did, right? And then just redraw this bond straight. So it's geometrically appropriate, right? If you don't do it, it's kind of okay. Your Ochem teachers will be okay with it. But to play it safe, make sure you draw it straight. So it's geometrical. I can't speak English, okay? You know what I mean, okay? So what I just basically did now is between every alpha and beta carbon we said, I just drew a double bond, right? We eliminated that alkyl halide, so it's no longer there, doesn't exist. And I just drew in a double bond between every alpha and beta carbon. So we have this one, we have this one, and this one, okay? So once again, so this one is corresponding with this one is corresponding with this, and this one's corresponding with this, okay? You will notice that this one and this one are actually identical. They're the same thing. Just because the double bond's in a different place, it's still in the ring. It's still the same molecule. So in other words, these are equal. So we really don't care about them, okay? We just care about one of them. So we can pick either if you want to go this one or this one. Does not really matter. Okay, now look at the base. Is it bulky? If it is not, the more substituted product, the Zaitsev, is a major product. So sodium methoxide is not bulky. So indeed, like I said, the Zaitsev product, which is the more substituted product, is the major product. Okay, so let's look at these two molecules here. You will notice that, okay, this is how you do it. What you need to do is look at the alpha carbon and look at the beta carbon and count how many branches are coming off of it. So we have this alpha carbon, right? One branch, 2 branches, right? We don't count this one. We don't count the one between the alpha and beta carbon, okay? Now this beta carbon has 1 branch to it. So 2 plus 1 equals 3. So this is a 3rd degree. So once again, we look at the alpha carbon as 1 branch, 2 branches, and then we look at the beta carbon as 1 branch. We do not count the one between the alpha and beta. So this is a 3rd degree. Now let's look at this one. This one, we start from the alpha carbon, we have 1 branch, 2 branch, and we don't count this. So, and the beta has no branches, right? So this is a secondary. This means that since this is more substituted, this is a 3rd degree versus a 2nd degree, this is known as the Zaitsev product and will be the major product because I said this is a non-bulky base. And since it's a non-bulky base, the more substituted product is the major. And this is the Hofmann product because this is the less substituted one. Let's do another example. Okay, so the first thing we should do is look at the base. Is it bulky? It is not bulky, so we immediately know that the product, the Zaitsev product, will be the major product. So here's how you do it in seconds. Just by looking at this molecule, I already know the answer. Actually, this may be a little bit more difficult, and you'll see why. So this is the alpha carbon, right? Because remember, this is the alkyl halide, right? This is the carbon directly bonded to the halogen. And now let's look at all our beta carbons. This is the beta carbon. This is a beta carbon, and this is the beta carbon. Okay. But you must be careful. Why can I not put a double bond here? Why is this not an acceptable answer, right? This looks pretty substituted, right? Like you would think this would be the Zaitsev product, but it's not. The reason is because this carbon right here has no available protons. It's all being taken up. It already has 4 bonds. There's no hidden hydrogen here, right? Then it would be 5 bonds. So remember, this has 1 bond, 2 bonds, 3 bonds, 4 bonds. No available protons. So this immediately eliminates the one of the answers. Okay? So it cannot, the double bond will not be here. So it's either going to be here or here. And hopefully, maybe you already see the answer. So, if I were to eliminate this, is how you watch how you do it. So all you have to do is just eliminate this, right? Actually, let me leave that for you. And then draw in our double bond here, right? How many branches does this have? 1, 2, 3. Okay, so this is a 3rd degree. If I were to do it like this. Now let me erase this. If I were to put the double bond here, how many branches is this? How substituted is this? Well, if you look at the alpha carbon, 1 branch and 2 branches. And this beta carbon has no branches. Remember, we don't count the one between the alpha and beta. This doesn't count. And there's no branches, right? You have no branches. This is a 2nd degree. That would mean this one would be the Zaitsev, okay? And would be the major, because it's a major because this is not a bulky base. And then if you were to put it here, this would be the Hofmann. Okay, so when you write this on an exam, actually, you know what? Let's do the arrow pushing. I realized we didn't do the arrow pushing. How would we do the arrow pushing? So, let's say, we go all the way back here. Okay, how would we do this? Okay, so here's what we do. When you do it on an exam, and we're just going to do, for example, let's just do the Zaitsev, for example. You must draw the hydrogen out from the beta carbon. Usually on exams, the hydrogen won't be there. You need to draw it in. Always, almost always, the oxygen is going to have the electron, okay? Unless it's the nitrogens, right, with the bulky bases. Remember this? Then the nitrogens have the electron. But in this circumstance, the oxygen has the electrons. Remember, sodium never does anything. So what's going to happen is the electrons are going to go, the and attack this and steal it, okay? The bond here dissociates and turns the double bond here. That's ugly. Okay. Now we would form this double bond, right? Well, now the carbon would have 5 bonds. So now this leaves like that. And that's how you would do it, okay? And now what we're left with is this. That, okay? Because remember, you have to include the leaving group. The base has now stolen the proton. So how do we draw that? Well, how you draw this usually is just ignore the sodium, pretend it's not there, and you draw it in like this. Just attach the hydrogen to the oxygen and include the rest of it except the sodium. Okay. Actually, you could draw it like this. Better to do it like that. Okay. And then you would draw in what we have. Okay, like that. And that is it. If you found this video helpful, please like and subscribe. Until next time, later.